So this is taken from the first worksheet in Unit 9, and we're looking at finding volumes of solid figures. First one is number 5 from that first worksheet, and it says find the volume of the truncated cone which is created from the given right circular cone. Okay. Recall that the volume of a cone is 1/3 the area of its base. Here our base is the circle, so pi r squared times the height. And so the first thing we're going to do is plug in those values for the larger cone and find the volume of the larger cone. So plugging this in, we get 1/3 pi times 6 squared times 15. Punch that into your calculator. So I'm going to type in 6 squared times 15 divided by 3. Don't multiply the pi, leave the pi alone, and you end up with 180 pi. So that's for the volume of the large cone. Now in order to get the truncated cone, we're going to have to cut the top off. When you cut the top off, the top itself is a smaller version of the larger cone. And in fact, the two figures are going to be similar because they're coming from the same exact cone. And so we see that what's left is a height of 10 if we're looking at the truncated cone on the left hand side, which tells us the height of the smaller cone is 5. And so if we compare heights, we get so we'll go small to large. We have a 5 to 15 ratio, or we can reduce that 1 to 3 ratio. So if we compare volumes, and we'll go small to large, well, heights are one-dimensional, volumes are three-dimensional. So to move from one-dimensional to three-dimensional, you cube it. So I'm going to cube, it's going to be 1 cubed to 3 cubed, which is 1 to 27. So that tells me that the volume of the larger the volume of the larger cone is 27 times bigger than the volume of the smaller cone. So we can quickly get the volume of the smaller cone by taking the volume of the larger cone. I'll put V with a little s for volume of the smaller cone, is the volume of the larger cone, 180 pi, divided by 27, because it's 27 times smaller. And we can reduce that. If we divide top and bottom by 9, we end up with 20 pi over 3. As a decimal, we get about, I'll round it, 6.7 pi. If you had trouble seeing that we should divide by 27, another thing we could do is, well, when we're comparing volumes, we can set up a proportion. We could say the volume of the smaller divided by the volume of the larger is 1 to 27, and you can cross multiply and you get 27 times the volume of the smaller is the volume of the larger. And so if we're solving for the volume of the smaller, you divide by 27, and you see that the volume of the smaller is the volume of the larger divided by 27. And so that's how I knew to divide by 27. So now let's put this together. What we're after here is the volume of the truncated cone. So the volume of the truncated cone is equal to the volume of the larger minus the volume of the smaller, which is 180 pi minus roughly 6.7 pi, which is about 173.3 pi. And if you multiply pi into that, we get 544, roughly 0.4, and we're talking about cubic units. Number 6, we have a truncated pyramid this time, and so we're going to kind of work through this the same way. We know that the volume of the truncated pyramid is the volume of the large pyramid minus the volume of a smaller pyramid, which we get when we truncate it. Okay, truncated meaning we're going to cut the top of that pyramid here, and we end up with a smaller pyramid. The top part that we cut off is a smaller pyramid. What we do know is the height that's left over is 4, and we don't see the original height of this pyramid. But if you look at the part I'm going to highlight, you see a right triangle. Which we can use to find the height of the large pyramid. So let's let h be the height of that large pyramid, and we know that h squared plus 6 squared is equal to 10 squared. The square of the sum of the squares of the legs of a right triangle is equal to the square of its hypotenuse. So h squared is 100 minus 36, which is 64. So take the square root, and h is the square root of 64, which is 8. So the height of the larger compared to the height of the smaller, well, the height of the larger is 8, and the height of our smaller, well, if the bottom part's 4, and then the top part's got to be 4, so 8 to 4, which we can reduce to 2 to 1. So that's one-dimensional. If we compare the volumes, we don't know them yet, but the volume of the larger compared to the volume of the smaller, which is three-dimensional. So we're going to cube those. So we take 2 to the third power and 1 to the third power, so that's 8 to 1. So if I say, well, the volume of the larger divided by the volume of the smaller is going to be 8 to 1. If I cross multiply, I get 8 times the volume of the smaller is equal to the volume of the larger. Divide by 8, and the volume of the smaller is going to be volume of the larger divided by 8. We'll come back to that. So let's find the volume of the larger. In general, the volume of a pyramid is 1/3 times the area of its base. It says this is a square pyramid, so the length of this base is going to be 12 because half of it is 6. So this is a 12 by 12 square. So we're going to say 12 times 12, that's the area of the base, times the height. We found the height of the larger pyramid is 8. So plug that into the calculator. 12 times 12 times 8. Divided by 3. And we get 384 units cubed. And that's the volume of the larger pyramid. The volume of the smaller pyramid we said is the volume of the larger pyramid, which is 384 divided by 8, which is exactly 48. And so now we can find the volume of our truncated pyramid. It's the volume of the larger, which is 384, minus the volume of the smaller, which is 48. And we get 336 cubic units. Number 8, we know that the volume of our cone is given. The radius of the lower base is given at 9. And we want the height of the original cone. The height of the truncated cone is 6 centimeters. And the radius, we don't know. Okay. So again, we're gonna break this up. We got the large cone and the small cone. The small cone is the part we don't see. It's the top here that was cut off. Okay. And so we're looking for the radius of the small cone. We have the radius of the large cone. Let's see, what can we compare? We have so we got the radius of the large compared to the radius of the small. We know the radius of the large is 9. We don't know the radius of the small, so I'll call that x. So that's one thing, we're looking for x. We got the height of the large compared to the height of the small, and we don't know either of those. Okay. We got the volume of the larger compared to the volume of the smaller, and the volume of the larger is 486 pi centimeters cubed. We don't know the other, I'll call that y. Okay. But we do have a formula for the volume of a cone. So the volume of the larger one we know is 1/3 times the area of its base, which is pi times r squared, so 9 squared, times the height. And so that's going to give us the height of the larger cone. plug that volume in. We got 486 pi equals 81 is 9 squared divided by 3 is 27 pi times h. Divide 486 pi by 27 and we get 18. And that's the height of the larger cone, so we know that's 18. And now we know the height of a smaller cone. The height of our smaller cone is, well, the truncated part is 6, so if the full height is 18, right? So this full height is 18, and we cut it, so there's 6 left on the bottom, so what's left on the top is 12. So we have the height of the smaller, and we can reduce that ratio, divide by 6, and we get a 3:2 ratio. And so now we can find everything else we need. So if it's a 3:2 ratio, this is one-dimensional. So is the radius. Radius is also one-dimensional. And so we know that the ratio of the radii are going to be this. It's going to have the same ratio for the heights, and that ratio of the heights is 3:2. So we know this is also 3:2. So that we can set up a proportion here to solve for our missing radius. We could say 9 over x is equal to 3/2. You can cross multiply and get 3x is 18. So x is got to be 6. And so let's see if we found what we were looking for. The height of the original cone, we got, so the height of the larger cone is 18 centimeters. We wanted that. And then we wanted the radius of the lower base, the radius of the upper base, which is the radius of the smaller cone, and we found that as 6 centimeters. Part B here is on density. This is taken from worksheet 2 of Unit 9 in Math 3. And we're going to use the density formula, which density is your mass over volume. So iron has a density of 7.87 grams per cubic centimeter. We want to find the mass, and we're given some values to help us find the volume. Here we have a rectangular prism. The volume is going to be 10 times 5 times 2, which is 100 cubic centimeters. And so our density, 7.87, is equal to mass over volume. And solve for mass. I'm going to put this over 1 and cross multiply, and you get mass is equal to 787. And then we want units. If you look at the density, it's grams per cubic centimeter. This is the units of mass. This is the units of the volume. And we're solving for mass, so we're looking at grams. Number 8, we got a cylindrical cake below that has a density of 2.285 grams per cubic centimeter. So again, we see the mass is in grams, the volume is in cubic centimeters. What's the mass of the cake? So let's find the volume of this cake here, which is the area of the base, so pi r squared times the height. So 10 squared is 100, so we have 1500 pi cubic centimeters. And so our density is mass divided by volume. They give us a density at 0.285. We don't know the mass. We got the volume at 1500 pi. So I'm going to cross multiply, and I get mass times 1, which is mass, is equal to 1500 pi times 0.285. So 1500 times 0.285 is 427.5 times pi. If you multiply that times pi, you end up with 1343, we're rounding here, roughly 1343, and we're looking at grams here. We got a bar of gold that weighs 29.4 pounds, so that's mass. If the density of gold is 0.7 pounds per inches cubed, what is the length of the gold bar? So we have density is mass over volume. Density is 0.7. Mass is 29.4, and we need to find our volume first. I'm going to cross multiply here, and I get 0.7 times the volume is 29.4. I'm going to divide by 0.7 and get 29.4 divided by 0.7. Use my calculator. To get 42. And we're looking at cubic inches. And so in our picture on the right, we know that the volume is our missing value, which we'll call x, times 3 times 2, and we know the volume, we just found it, is 42. So 42 is equal to 6 times x, divide by 6, and we get x is 7 inches. 11 deals with population density, which uses a very similar form. It's not exactly mass and volume, but let's take a look here. The city of Clovis has a population density of approximately 5,000 people per square mile. And so what we're going to work on here is, instead of saying the density is mass over volume, we're going to say the density, the population density, is the population size it's kind of like the mass over the size in which that population occupies, or the land, in this here is square miles. So area occupied. Okay, and so that's what we're going to use here. So when it tells us 5,000 people per square mile, right there, that's density. Okay. So if the area of Clovis is 24 square miles, what's the population? So we could say our density, 5,000 is our population size divided by 24, which is the area in which it occupies. We can cross multiply and get our population is 5,000 times 24, which is 120,000, and our units are people. Okay, so that is part A. Part B, if there are on average 3 people per household, how many households are there? So for part B, we found that there are 120,000 people. Divide that by 3, and we get roughly 40,000 homes or households. And then part C, recent trends predict that in the next 10 years the population will increase by 20,000. In order to maintain the same population density, how many additional square miles must be annexed by the city? So if we add 20,000 to our population, so we're going to have 120,000 originally plus 20,000 more, divided by, I'll say, the area, and we want to keep the same population density, which is 5,000. And so if I cross multiply here, I'm going to get the 5,000 times the area is 140,000. Divide 140,000 by 5,000. We get 28 square miles. And right now we got 24 square miles, so how many more? If we want 28 and we have 24, we need 4 more. 4 square miles. This is part C on quadratics, taken from the 3rd section in Unit 9. We're going to look at number 2. A rectangular pen is made with 50 meters of fencing on 3 sides. The 4th side is a stone wall. Find the greatest possible area of such an enclosure. So here's our stone wall. Here's our fence. Rectangular, and it's got some length, capital L for length, and some width, W. Find the greatest possible area. So in the perimeter of this fence, we know that W plus W plus L is got to be our 50 meters of fencing, or 2W plus L is 50. We want the greatest possible area. We know the area of a rectangle is length times width. So in our 2W plus L equals 50, we could solve for L and get L as 50 minus 2W. So the next step is to substitute that 50 minus 2W in for L. So we know the area is length times width. Instead of writing the length times width, we're going to substitute in the 50 minus 2 times W here. And now we can distribute the W here to 50 and negative 2W. And we get the area is equal to 50W minus 2W squared. I'm going to rewrite it as the area is negative 2w squared plus 50w. To give you a visual here, so this is the width that we use in the area. We get this upside down parabola. That's our equation, a equals negative 2w squared plus 50w, where the vertex is at the maximum here. So if we can find the vertex of this, then we can solve. So we want to put this in vertex form. I'm going to factor out the negative 2, and I'm left with w squared minus 25w. So then we want to complete the square here. We take half of the negative 25 and square it. So we're going to get 25 times 25, which is 625, over 2 times 2, which is 4. This really has a value of negative 2 times this value. So negative 2 times 625 over 4 is going to be negative 625 over 2. So that's what I'm going to add. 625 over 2. And then we can factor this. And we get the area is equal to negative 2 w minus 25 over 2 squared plus 625 over 2. So our vertex is 25 over 2 comma 625 over 2. The first number stands for our width, the second number stands for our maximum area given that width. So it said find the greatest area, 625 over 2, which we can write as a decimal, 312.5 square meters. Number 8, an arrow is shot vertically upward with an initial speed of 64 feet per second. Its height after t seconds is given by h equals 64t minus 16t squared. How high does the ball go? I'm going to rewrite that equation as h is equal to negative 16t squared plus 64t. I'm going to put this in vertex form. This is a quadratic. Again, we get that picture. I'll draw it down here. We have the height of that ball over time, and so that ball creates this parabola. And the vertex is where we have our highest point. So I'm going to focus on getting it in vertex form. Factor out the negative 16. You get t squared minus 4t. Leave a little room to complete the square. We cut 4 in half and square it. We end up getting 4, so I'm going to add 4 here, which really has a value of negative 64. So I add 64. And now factor, so the height is negative 16 times t minus 2 squared plus 64. Our vertex is going to be 264, where 2 is the time in seconds, and 64 is our maximum height. So now if we look at part A, it says how high does the ball go? It goes 64 feet. How many seconds does it take to reach the maximum height? 2 seconds. Both of those came from our vertex. When does the ball hit the ground? Now, vertex form doesn't help us when the ball hits the ground. When the ball hits the ground in our picture, that is at an x-intercept. And so we're going to go back to our original equation. H equals 64t minus 16t squared, and plug in 0 for the height, because that's when it's hitting the ground. I'm going to try to solve this by factoring. I'm going to factor out it's enough to just factor out a t. We could have factored out 16 or negative 16 as well, but this will work. And so we end up with either time is 0 or 64 minus 16t is going to equal 0. Solve the second one. We get negative 16t is negative 64. Divide by negative 16 and you get t is 4 seconds. So when does the ball hit the ground? Either at 0 seconds or 4 seconds. 0 seconds is when the ball is hit, and 4 seconds is when it lands. And there's a little issue here, which starts by talking about an arrow shot vertically upward, and then now it's talking about a ball. It should say arrow. And so our answer is 4 seconds. Number 12, the equation for height, h, of an arrow is h equals negative 3/4 t squared plus 6t plus 6, where t represents time in seconds since shooting the arrow. Find the time needed for the arrow to reach its maximum point. So we're talking about a vertex when you hear maximum. And then how high will it go? Again, that's talking about the vertex. So if we find the vertex, we answer both these questions. So h is equal to negative 3/4 t squared plus 6t plus 6. I'm going to get rid of the fraction first by multiplying everything by 4. And I get 4 times h is equal to negative 3t squared plus 24t plus 24. And then I'm going to factor out the negative 3 from the first two terms and get 4h is negative 3 times t squared minus 8t. Leave a little room to complete the square, keep the positive 24 at the end. Complete the square, we take the negative 8, cut it in half, and square it. Get 16, which really has a value of negative 3 times 16, which is 48, negative 48. So we're going to add 48 at the end here. So now 4 times h is negative 3. Factor this to t minus 4 squared. Plus add 24 and 48 together to get 72. And then the last thing to do is to solve for h. So we're going to divide by 4. You divide these three pieces by 4. And you get the height is negative 3/4 t minus 4 squared plus 4 goes into 72 18 times. So our vertex is 418, where 4 is our time and 18 is our height. So find the time needed for the arrow to reach its maximum point. It took 4 seconds. How high will it go? 18. And our units here, it doesn't specify, so I'll say 18 units. I guess, yeah, it does say seconds for time, so I'll use seconds. So we'll stop there. This is part D on the scale factors of similar figures. And this is taken from section 4 of, or worksheet 4 of Unit 9. So first, height and perimeter are one-dimensional. It's important to realize that. Area, whether area of the base ratio or surface area, all area is two-dimensional. And volume is three-dimensional. And so when you're looking at ratios of two figures, so we got figure A and figure B, and their height ratios are 3 to 5, that's their one-dimensional ratio. All one-dimensional ratios stay the same, so the perimeter ratio would also be 3 to 5. To go from one-dimensional to two-dimensional ratio, you square those. So we get 3 squared and 5 squared, which is 9 to 25, which would be the same as the surface area ratio. And to get a three-dimensional ratio, you cube the one-dimensional ratio. So it would be 3 cubed to 5 cubed, or 27 to 125. In the second column, we got a 2 to 7 ratio. That's one-dimensional. Perimeter is one-dimensional. So the height's also going to be 2 to 7. That's one-dimensional. The area of the base and the surface area are going to be 2 squared to 7 squared, which is 4 to 49. And the volume ratio is going to be 2 to the third to 7 to the third, which is going to be 8 to 343. In the third column, we have area of base ratio 4 to 9, so the surface area ratio is also going to be 4 to 9, because those are two-dimensional. To go from two-dimensional back to one-dimensional, you take the square root of 4 to the square root of 9, which is going to be 2 to 3. And to find the volume ratio, you cube the one-dimensional ratio. So 2 cubed to 3 cubed, which is 8 to 27. In order to go from two-dimensional to three-dimensional, we need that one-dimensional step. So you go back to one-dimensional and then move forward to 3 dimensions. In the last column, we have the three-dimensional ratio 1 to 8. And you're going to want to go first from three-dimensional back to one-dimensional by taking the cube root of 1 and the cube root of 8, which is 1 to 2. That's your one-dimensional ratio. And then square that to get the two-dimensional. So we get 1 to 4 for our two-dimensional ratios. Alright, in number 1 here, we have two bottles that are mathematically similar. The smaller one is 6 centimeters high and holds 30 I think it should say milliliters. I think we got a misspell there though. of perfume. The larger one is 9 centimeters high. What's the volume of the larger one? So we have a comparison of heights. Remember, height is a one-dimensional thing, and we have a ratio 6 to 9, small to large, and we can reduce that ratio if I divide by 3. 6 divided by 3 is 2, 9 divided by 3 is 3. So 2 to 3 is my one-dimensional ratio. We want to talk about volume, which is three-dimensional. So if we know our one-dimensional ratio, we can get our three-dimensional ratio by cubing the 2 and the 3, and we get 8 to 27. And we know that the smaller one holds 30 milliliters. Okay, so smaller is 30, and we have x for the larger one. So we're going to take these two right here, the 8 to 27 and the 30 to x, and we know those are equal to each other, so we set up a proportion. 8 over 27 is 30 over x, and cross multiplies. 8x equals 30 times 27, or 8x equals 810. 810 divided by 8 is 101.25, and we're looking at milliliters. That's our volume. Number 2, the two boxes below are similar and both have to be wrapped with decorative paper. If it requires 5 square yards of paper to cover the larger box, calculate the amount of paper needed to cover the smaller box. Notice what's drawn in is they show you the heights. So we're given the heights in the diagram, which is one-dimensional, and we got 24 to 15. We can reduce those, divide them both by 3, we get 8 to 5. So that's our one-dimensional ratio. In the question though, we need to know the amount of paper needed to cover the small box. And if you look at the units for the paper, it's yards squared, which is indicating two-dimensional. This is a surface area type idea. Covering the surface. So this is two-dimensional. And if we have our one-dimensional ratio 8 to 5, we can get our two-dimensional ratio by squaring those. So 8 squared to 5 squared, or 64 to 25. They tell us it takes 5 square yards to cover the larger box. So I'm going to put 5 first because we're going large to small in this problem. And we're looking for how much paper is for the smaller. So here, I'm going to take these two ratios, set up a proportion. 64 over 25 is equal to 5 over x, and cross multiply. So 64x equals 25 times 5, or 64x is 125. X is 125 divided by 64, which is, I'm rounding here, 1.953 square yards. Number Number 3, the figure to the right is of two shampoo bottles that are mathematically similar, and the cost of the shampoo depends only on the volume of liquid in the bottle. If the small one costs $3, what should the large one cost? Okay, so again, in the picture, they show you the comparison of heights. Remember, heights is a one-dimensional thing. And we have the small to large ratio 18 to 27. We reduce that ratio dividing by 9 and get 2 to 3. If you read the problem, it's talking about volume and the cost related to volume. Volume is a three-dimensional thing, and so we can get our three-dimensional ratio by cubing the one-dimensional ratio, so 2 cubed to 3 cubed, or 8 to 27. The small bottle costs $3, so 3 goes with the small because that's the price is related to the volume. We don't know what the cost of the larger one should be, so we're going to take those and set up a proportion here. 8 to 27 is 3 to x, and cross multiply. 8x is 3 times 27, or 8x is 81. So x should be 81 divided by 8. And we're rounding a little bit here, so it's $10.13. Section E on cross sections. This is taken from the 5th section in Unit 9, and we're looking at number 2 from that worksheet. And so we have a cylinder here, and A is going to cut this cylinder horizontally. B, we're going to cut it vertically, and we want to see what shapes we have. To help you visualize this a little bit better here, I have a cylinder up in GeoGebra, and you can see we have this cross section that I'm moving up and down, and you can see as it intersects the cylinder, it's creating that circle shape. Whereas if I rotate that to vertical and move that around, you see that it has a rectangular shape. And so going back to our problem here, at A we get a circle, B we get a rectangle. For 3, we're going to look at a cone. A, we're going to cut it diagonally. B, we're going to slice it horizontally. And then C, we're going to cut it vertically. And so again, let's get a visual here. Here's the horizontal. We see that when you cut it horizontally, it's a circle, no matter what height. Changes the radius of that circle, but it's a circle. As we rotate it a bit, it's no longer a circle, but it's an ellipse. So it's kind of a squished circle. And then as we continue to do this, let's move it over a little bit, we get a parabola. So let's write that in. So A was the diagonal cut, we had an ellipse. B, we had a circle. And C, we had a parabola. Number 9, we're asked to draw and describe the solid of revolution formed by rotating the right triangle about the cylindrical axis of revolution. Find the volume for parts A and B. So for part A, we're going to revolve it around the x-axis. Here's the x-axis. So you got to picture it hinged to the x-axis, and so it begins to circle around, and so you have it mirrored down here, but then it's 3D, so it comes out, you have this, and it's rotating around in a circle here. So I don't know if you can picture this, but you see it's a cone on its side. So we have a cone with a radius of 2, because the radius goes from the center at 0, 0 up to the edge of the circle, and the height is going to be 3 because it goes from 0, 0 to 3, 0. And so we can say the volume is 1/3 pi r squared times the height. Which is going to be 4 pi. Now let's take a look at what happens if we rotate this around the y-axis. So to demonstrate, I'm going to erase my picture here. And now it's hinged at the y-axis. So as I spin it around, over here at -3, we'll have this reflection across the y-axis, and it's rotating around, so we try to get the three-dimensional shape around it here. So it's rotating. This is the base rounding in a circle, and then the whole thing is just rounding in a circle. And so we get this cone shape again, where if you look at the base, which is a circle, the radius is from the center, 0, 0, to the far right, and so we see it's a cone again with a radius of 3. And the height is from this dead center at 0, 0 all the way to the top, which is at 2. So the height is 2. And so the volume is going to be 1/3 area of the base, which is a circle, so pi r squared, so pi times 3 squared, times the height, which is 2. Sorry, I put 1/2, it should be 1/3. And so we multiply this out, we're going to get 6 times pi. Last one for each. So for number 11 here, we're going to draw a two-dimensional shape that would be revolved about the indicated axis to generate the solid. So on this one, we're going to revolve it around the x-axis to create this this bowl shape. Okay, and so anywhere on the x-axis, it doesn't really matter where we start. I'll start at 0, 0. I'm going to draw. So if I cut this right down the middle, I'm going to be drawing this top half here. Okay, and so really what I'm going to do, I traced it. I'll grab that piece, bring it right over here to the x-axis, and so that's all we need. So if I revolve that and spin that around the x-axis, it's going to generate the shape we have here. Notice that I don't want to close the top. I don't want to do this because it's an open bowl. We want that container to be open. So I'm going to leave that top open so that we have an entrance into the container after this thing's spinning around.